Hi, my dear student. Hope you are doing good, and I want to take this opportunity to welcome you to this lesson. We are talking about radioactivity, and in this lesson, we want to look at nuclear reactions. Remember, in the earlier lesson, we were able to see that during radioactivity, when a particle is undergoing radioactivity, it emits three types of radiations, namely alpha, beta, and gamma rays. So we were able to see the properties of each of those particles. And when it comes to alpha particles, we saw that one of the properties is that when writing a nuclear equation using alpha particles, we said that alpha particles are represented with a helium atom with a mass number of 4 and atomic number of 2. That is, if a particle undergoes radioactivity by emitting alpha particles. For beta particles, we saw that if you're writing a nuclear equation, you use an E electron with a mass number of 0 and atomic number of -1. So, my dear candidate, I want us to see how we write a nuclear equation. So before we look at examples, I want us to understand this, that anytime a particle emits, anytime alpha particles is emitted, there is a change in both atomic number as well as mass number. So this is what I mean by that. When an atom decays by emitting alpha particles, when a particle decays by emitting alpha particles, this is what happens to the mass number. The mass number of the new particle, mass number of the new atom, will reduce by 4, while the atomic number will also reduce, but it will reduce by 2. That means if you're writing a nuclear equation when alpha particle is emitted, so for the new particle you reduce the mass number by 4 and you reduce the atomic number by 2. When it comes to beta particles, when they are emitted during that process of disintegration, then the mass number does not change. Mass number remains, but what changes is the atomic number. The atomic number is normally increased by 1. So atomic number increases by 1. Now for gamma rays, the mass number and atomic number is not affected, so it remains the same. So having said that, I would like us to look at examples of nuclear equations. So let's start by this example here. Examples of nuclear equations, so that we see. Remember, my dear student, if you're writing a nuclear equation, the sum of atomic number on the left of your equation should be equal to the sum of the atomic number on your right of the equation. The same applies to mass number, should be equal on both sides of the equation. So let us look at this example here. So we have this equation here: a particle of lead whose mass number is 210, atomic number 84, decays by emitting beta, not beta really, but alpha particle. Remember, we have said alpha particles are represented using a helium with a mass number of 4, and atomic number of 2. So my dear candidate, like we have said earlier, we have to balance the mass number on the left as well as the mass number on the right. So a new particle will be produced. So it's just a matter of, remember you have said, if an alpha particle is emitted, the atomic number will reduce by 2. So initially, the atomic number is 84. So we shall reduce 84 by 2, and that will give you 82. And then this is the atomic number. Then the mass number, we have said, will reduce by 4. So initially it was 210. So you reduce it by 4, you will get 206. So my dear candidate, you realize that if you add the atomic numbers on the left of the equation, it should be equal to the atomic number on the right of the equation. So on the left, atomic number 84. On the right, this is 82 plus 2, that will give you 84. Mass number on the left, 210. Mass number on the right, 206 plus 4, that will give you 210. So this is what is called a nuclear equation. So don't forget, if an alpha particle is emitted, we reduce the mass number by 4 and the atomic number by 2, like that. So another example of a nuclear equation. Suppose a beta particle is emitted. How will the equation look like? I want us to consider this particle here, represented by letter TH. This one has a mass number of 232 and an atomic number of 88. So we have been told that this particle decays by emitting a beta particle. Remember, you have said if a beta particle is emitted, the mass number does not change, but the atomic number will be increased by 1. So we are going to have a new particle like that, and then in the process there is emission of a beta particle, which is represented in a nuclear equation with that. So the new particle will have an atomic number of what? Remember, you have said we increase the atomic number by 1. So on the left it is 88. On the right we increase it by 1. That will give you 89. Then what about the mass number? We have said the mass number when a beta particle is emitted, it does not change. So this will remain as 232. So this is another example of a nuclear equation. Once again, don't forget, the mass numbers on the left should be equal to the mass numbers on the right. You can just confirm that. On the left it is 88 atomic number. On the right 89 plus negative 1. Using a mathematics, you will get 88. On the left, mass number 232. On the right, 232 plus 0, that will give you 232. So this is another example of a nuclear equation. Another example of a nuclear equation. Suppose we have more than one alpha or beta particle being emitted. How do we write the nuclear equation? So I want us to consider this one here. We have this particle represented by letter Cn. Mass number is 285 and atomic number 112. It decays to produce another particle, which is represented by letter Hs with the emission of two alpha particles. So we put here 2, then you write the alpha is He, mass number 4 and atomic number of 2. So we need to get the mass number of the new nuclide as well as the atomic number. So it's just a matter of balancing the atomic number as well as the mass number. So you check on the left, I have a total of mass number 285. On the right, I should also have the same. So that means I will now take 2 multiplied by 4, because we are emitting 2 alpha particles. So I multiply this one by 4, then I reduce by the value. So when you multiply 2 by 4, you get 8. So I reduce 285 by 8, and that will give me 277. So the new nuclide will have a mass number of 277. So that when I add 277 plus 8, I will get 285. What about the atomic number? On the left, atomic number is 12, 112. On the right, now that you are emitting 2 alpha particles, which I'll multiply 2 by 2, that will give you 4. Then I reduce the atomic number by 4 because we are emitting 2 alpha particles. So this will be 112 minus 4. That will give you 108. So my dear candidate, if you add 108 plus 4, you will get 112. So this is another example of a nuclear equation. Suppose we have 2 beta particles being emitted. How do you handle such a question? So we have this particle represented by TH decaying to emit another nuclide. So initially this one has a mass number of 212 and an atomic number of 96. So it decays by emitting, we have been told, 2 beta particles. So we are going to put 2, then beta represented by mass number 0, atomic number negative 1. So we are supposed to make sure that the mass numbers on the left are equal to the mass numbers on the right. So mass number on the left 212, on the right we are supposed to get this value here. So we are going to take 0 multiplied by 2, that will give you 0. Then I reduce this 212 by 0, I will still get 212. And then come to atomic number. On the left it is 96. Then it means I should also have 96 on the right hand side. So now that we are emitting, there is emission of 2 beta particles, which I'll multiply 2 by -1, that will give you -2. And then you increase this value by 2. So we are going to take 96 plus 2, the one we are getting here, and that will give you 98. So that means the new nuclide will have an atomic number of 98 and a mass number of 212, like that. So these are examples of what you are calling nuclear equation. So I want us to look at something that is related to that, and that is called radioactive decay series. Radioactive decay series. So when we talk about a series, it means decay is happening in several steps. We have seen a nuclide that is unstable will undergo radioactivity to produce a stable nuclide. So it happens sometimes that the new nuclide might be radioactive and unstable. So in that case, it will undergo further decay until we get a new stable nuclide. So as a result, it will lead to several chain reactions, and that is what you are calling radioactive decay series. So this one happens when a radioactive substance undergoes several decay processes until a stable nuclide is obtained. So I want us to consider this radioactive decay series here. We want to consider this so that we are able to identify the particles which are emitted in every step. So consider the decay series. Consider the decay series below. consider the decay series below. So we have this. Decaying to produce this. So we are saying this one happens until a stable nuclide is obtained. So it is a series. It occurs in several steps. So my dear candidate, I want us to be able to identify the particles which are emitted in every single step. I want us to be able to identify the particles which are emitted in every single step of this decay series, so that you should be able to balance in terms of mass number of the new nuclide and atomic number. So this is what you're calling a radioactive decay series. So you can see it's taking place in several stages. So the first one has a mass number of 238 and atomic number of 92. So it decays to produce a new nuclide with a mass number of 234 and atomic number of 90. This one undergoes further decay to produce another particle, mass number 234, atomic number 91. It undergoes further decay to produce a new one, mass number 234, atomic number 92. This one also undergoes further decay to produce another one, mass number 230, atomic number 90. It undergoes decay once again to produce a new one, mass number 226, atomic number 88. It undergoes further decay to produce a new particle. We are saying this one happens until a stable nuclide is obtained. That one also undergoes further decay to produce a new one, mass number 218, atomic number 84. This one undergoes further decay once again to produce a new one, mass number 214, atomic number 82, which also undergoes further decay to produce a new one, mass number 218, atomic number 283. Further decay to produce a new, mass number 214, atomic number 84. Further decay to get a new nuclide, mass number 210, atomic number 82. Further decay produce Bi, that is bismuth, atomic number 210, mass number atomic number 83, mass number 210. Further decay to produce 210, atomic number 84. Lastly, lead, mass number 206, atomic number 82. So my dear candidate, I want us to use this radioactive decay series to identify the particles which are emitted at every single stage. So we said we do that by just considering the mass number and atomic number. We have seen if alpha is emitted, the atomic number will reduce by 2, but the mass number will reduce by 4. For beta, mass number does not change, but atomic number is increased by 1. So we just check the mass number and atomic number. So considering the first part, you can see the atomic number has been reduced by 2 from 92 to 90. The mass number has also reduced by 4 from 238 to 234. That means there is a reduction. Mass number 4, atomic number 2. And this represents which particle, my dear candidate? That represents helium. and that is alpha. So that means when this particle is decaying, there is emission of alpha particle. So that is in the first case. Second case, check. Mass number has remained the same, 234, 234. Atomic number has increased from 90 to 91. So what does it mean? It means there is emission. Remember we said a beta particle, when it is emitted, the mass number does not change. What changes is the atomic number, and it increases by 1. So that means during this decay, there is emission of a beta particle. How about this one? You can see the mass number is 234. The atomic number is the mass number 234, also 234. Atomic number has increased from 91 to 92. That means once again, which particle is emitted? That is a beta particle. How about this one? Mass number has reduced from 234 to 230. Atomic number has also reduced from 90 to 92. Mass number reduced by 4. Atomic number reduced by 2. So that should tell you that there is emission of alpha particle. So we are saying the process takes place until a stable nuclide is obtained. So how about this one? You can see the mass number has reduced from 230 to 226. Atomic number reduced from 90 to 88. That means there is emission of a beta, not really beta, but alpha particle. Yeah, that's good. How about this one? The mass number has reduced from 226 to 222. Atomic number 88 to 86. Which particle is that? Once again, that is alpha particle. Here, mass number 222 to 18. It has reduced by 4. Atomic number 86, 84. It has reduced by 2. Which particle is that? Alpha particle. It undergoes further decay. Mass number has remained the same, 214, 214, but atomic number has increased. So which particle is that? That is a beta particle that is released. How about this one? Mass number remains 214, 214. Atomic number has increased, 83 to 84. Which particle is that, my dear student? That is beta particle. This one, mass number has reduced from 214 to 210 by 4. Atomic number has reduced by 2 from 84 to 82. The particle that is emitted is alpha particle. How about this one? Mass number 210, 210. It has not changed. So automatically that should tell you that that is a beta particle. Remember I said beta particle, the mass number does not change. How about this one? Mass number 210, mass number 210, atomic number 83 to 84. That means there is emission once again of a beta particle. Lastly, this happens to be the stable nuclide because the decay has stopped here. So this is the stable one. So mass number from 210 to 206, it has reduced by 4 from 84 to 82. That should tell you there is emission of alpha particle. So this is what is called a radioactive decay series. So my dear student, we have learned that when writing nuclear equations, if there is emission of an alpha particle, the mass number reduces by 4, atomic number reduces by 2. If there is emission of a beta particle, the mass number does not change, but the atomic number is increased by 1. So I want you to try the following questions. So the first question is as follows. Complete the following nuclear equations. Complete the following nuclear equations. First one is this. We have this particle whose mass number is 251 and atomic number of 96. It decays to produce a new particle whose mass number is 251 and atomic number of 97. So identify the particle that is released there. Part B, I want you to try this one. Again, this one is decaying, mass number 226, atomic number 88, producing a new nucleide whose mass number is 210 and atomic number of 80. Complete and find out the type of particle that is released and how many could they possibly be. And then lastly, you try this one. Part C, we have this one, decaying, mass number 228, atomic number 88, to produce a new nucleide represented by TH, mass number 228, atomic number 92. And then you find out which particle is released. So we have come to the end of our lesson, and I want to thank you for being attentive, and I'll see you in the next lesson. Thank you so much.